Have you ever, like, looked at something tiny, maybe a beetle, and then looked up at a huge skyscraper and just thought, is there some kind of hidden logic, a code that connects how everything grows?
That's a really deep question.
Yeah.
And it actually goes back, well, centuries. Even Galilei 400 years ago, he had thoughts on this.
Galileo on giant monsters.
Yeah, exactly. He pretty confidently said that, those massive movie monsters like Godzilla couldn't happen. Impossible.
Wow. Okay, but how could he know that back then? What made him so sure about something that didn't even exist?
Well, he noticed something really fundamental about how things grow. Weight. It increases way faster than height.
Faster? How much faster?
Think about a kid. Maybe they double in height, right? Say 90 centimeters to 1.8 meters. But their weight, it might jump 5 times, maybe 30 pounds to 150 pounds.
Oh, I see. So the weight just balloons compared to the height.
Exactly. And Galileo realized if you just keep scaling that up, eventually any creature would just get crushed by its own weight. He wrote about it in his big work, Discourses and Mathematical Demonstrations, relating to 2 new sciences.
So it was a basic law of physics he uncovered just by looking at growth and scale. That's pretty powerful.
It really is. And it gets right to this core idea we're exploring today. The idea that things don't just get bigger copies of themselves. Like the book we're digging into says, bigger is different.
Right. New rules kick in at larger sizes.
Precisely. And that's what we're doing today. We're going deep into this amazing book called Scale by Geoffrey West. He used to head up the Santa Fe Institute, a real pioneer in complex science.
Okay, so our mission is to unpack this complex stuff, right? Make sense of the hidden logic behind growth, whether it's us, our bodies, or even like huge companies.
That's the plan. To open that door for you, help you see these underlying patterns.
All right, let's start close to home then. Our own bodies. Life itself. The main idea here seems to be that everything alive, it hits a wall, eventually. There are limits, right? Size, weight, even how long we live.
Yes, absolutely. There are fundamental limits. And the logic behind it is, well, kind of elegant when you break it down. It's all about how different parts of a system relate to each other as it gets bigger.
Like that cube example.
Exactly like the cube. Double the side length and the surface area goes up 4 times. But the volume, that goes up 8 times.
Yeah.
Volume grows much, much faster.
Okay, so if we think about us, height is like the side length, 1 dimension. Skin is surface area, 2 dimensions. And our weight, that's like the volume, 3 dimensions.
You got it.
So our weight increases way faster than our skin surface area. Does that mean, like, our skin struggles to keep up with our insides as we grow? Is that the problem?
That's a really good way to put it. You've nailed the core challenge. The crucial thing isn't getting lost in the exact mass, the exponents and all that, but seeing the principle. To understand growth in life, you need the driving force.
And for life, that's energy, metabolism.
Precisely. Our metabolic rate, the total energy we take in and use. Because every new cell, every bit of growth needs energy. And that difference in how surface and volume scale, it creates a bottleneck, a real limitation.
And this energy thing connects to a discovery back in the 1930s, Kleiber's law.
That's right. Max Kleiber, a physiologist back in 1932, he looked at tons of animals, pigeons, goats, oxen, all different sizes, and he found this incredibly consistent pattern.
Which was?
Their metabolic rate scales with their body weight, but not directly. It scales to the power of 3/4.
3/4. Okay, what does that mean in, like, real terms?
It means bigger animals are surprisingly efficient. Think about an elephant. It might weigh 10,000 times more than a mouse.
Right.
But it only needs about 1,000 times the energy. Not 10,000 times, only 1,000.
Wow. So 10,000 times heavier, but only 1,000 times the energy cost. That is efficient.
Hugely efficient. This relationship, Kleiber's law, shows that as life gets bigger, it gets much better at using resources.
Okay, so let me see if I get this. As we grow, we need more energy, obviously, but the amount of energy we get increases slower than our actual body mass does because of that 3/4 power thing.
Exactly.
So eventually, you reach a point where all the energy you take in is just enough to keep your existing cells going.
Yeah.
No extra energy left for making new cells.
You've got it. That's the biological limit to growth. It's kind of like a bathtub filling with water while the drain is open.
Okay.
At first, the water flows in faster than it drains out, so the level rises. But as the level gets higher, the pressure makes the water drain faster. Eventually, the draining speed matches the filling speed.
And the water level just stops rising. It hits an equilibrium.
That's exactly it. That's biological growth. You hit that point where it's all about maintenance, not expansion.
And this ties into lifespan, too. How?
Well, just living causes wear and tear, metabolism, blood flowing through vessels. It creates friction, damage over time. Larger animals often have more developed, more robust systems to handle this.
So the damage builds up slower, allowing for longer lives.
Generally, yes. But there's still a limit. Things still break down. Actually, Jeffrey West did a calculation based on these scaling laws for the theoretical maximum human lifespan.
Okay, fine.
Around 125 years.
125, okay. But you said Kleiber's law was based on observation, right? He saw the pattern.
Yes, it was inductive reasoning. Observing the pattern and making a rule, like seeing the sun rise every morning and concluding it always will.
But that doesn't explain why. Why that specific 3/4 number? Is there a deeper reason? A deductive logic?
That is the million-dollar question, and it leads us into some really fascinating, almost weird territory.
Okay, I'm ready. Lay it on me.
Right. So we live in a 3D world, don't we? Length, width, height.
Yep, 3 dimensions.
But when you look at these biological scaling laws, metabolism, yes, but also things like brain capacity, heart rate, the number that keeps popping up in the math isn't 3, it's 4.
4? How can that be? Where does a 4th dimension come from in biology?
That's the puzzle. To prove that 4 is right from first principles, we need to show that something vital in our body is effectively operating in 4 dimensions.
Whoa, okay. 4-dimensional biology. How do we even start thinking about that?
The key concept here is something called fractals.
Fractals. Okay, I've heard of those, like complex patterns that repeat themselves.
Exactly. Self-similarity, where the pattern looks similar whether you're zoomed way in or zoomed way out. Think of a coastline on a map.
Right. Zoom in and it's still jagged and complex. It doesn't smooth out.
Or a snowflake. That intricate pattern is there at every scale. Even stock market charts can show fractal behavior. A pattern over an hour might look oddly similar to the pattern over a year.
Nature's repeating patterns. Okay, I get fractals. But how does that relate to growth in dimensions?
Well, here's the crucial bit. Growth in nature often is a fractal process. It's not just about getting bigger overall. Think about how a snowflake forms. It continuously adds to its structure in that same repeating branching way.
Or a tree growing branches.
Perfect example. Or our own blood vessels branching out, smaller and smaller. It's growth through continuous fractaling.
Okay, so things grow by repeating fractal patterns, but how does that add a dimension? That's the part that's blowing my mind.
Right, it's definitely counterintuitive. But imagine taking a simple line, just 1D. Now imagine it starts folding and branching in on itself over and over, becoming incredibly intricate.
Okay.
If it does this enough, this line can actually start to fill a 2D space, like a square. It's still fundamentally a line, but its fractal pattern becomes so dense, it effectively takes on area, a 2D property.
So the fractal process itself can kind of bump up the dimension.
In a way, yes. There's actually a concept of fractal dimension, which doesn't have to be a whole number. But if a fractal structure completely fills the space it's in, it effectively gains a dimension. A line filling a plane acts like it's 2D.
Okay. My brain is stretching. So how does this apply to us, to our bodies? Is something inside us doing this?
Yes. The key is our circulatory system, our blood vessels.
Ah, the branching network.
Oh, exactly. First, observe that it is a perfect fractal. From the huge aorta down to the tiniest capillaries, the branching pattern repeats. It's self-similar.
Okay, that makes sense. It looks like a fractal tree.
Second, and this is vital, this network goes everywhere. It permeates our entire 3D body. It has to deliver oxygen to every single cell. It fills the space.
So, wait. The blood vessel network is a fractal.
Yep.
And it fills our 3D space.
Which means its fractal dimension isn't 3, it's effectively 4D.
Wow. That's incredible. So that's the 4 in Kleiber's law. It comes from the effective dimension of our circulatory system.
That's the argument Jeffrey West and his colleagues developed. It provides that missing deductive, bottom-up explanation for the 3/4 power law. It's not just an observation. It's rooted in the fundamental fractal geometry of life's distribution networks.
And it applies to all life, because all complex life needs these kinds of distribution networks.
That's the idea. It suggests that this 3/4 scaling of metabolism is a universal principle stemming from the physics and geometry required to sustain life in 3 dimensions.
Okay, that's a huge realization. But it also feels a bit deterministic, like our biological fate, our size, our lifespan, it's all kind of pre-programmed by these scaling laws.
To a large extent, for purely biological organisms, yes. The constraints are very real. Our maximum potential seems largely set by these physical and geometric rules.
But we're not just biological organisms in that sense, are we? We build things. We create societies.
Exactly. And that's the crucial pivot. Humans have this unique ability through tools, technology, social structures to kind of intervene, to
Mhm.
build things that operate on different scaling principles. We shape organizations.
Which brings us to the next big area, the growth of human systems. Companies, cities, even nations. Do they follow similar scaling laws? Or different ones?
They follow scaling laws, but with some fascinating twists. Let's explore this with a maybe a fun thought experiment. You familiar with the movie The Wandering Earth?
Vaguely, yeah. The one where they try to move the Earth because the sun is dying.
That's the one.
Yeah.
So big crisis, sun's going out. Two main options proposed. Option one, strap giant engines onto Earth and literally fly the whole planet out of the solar system to find a new sun.
Option 1, the Wandering Earth plan.
Okay, option two, build a massive spaceship, basically an ark, load up as many people as possible, and leave Earth behind.
Option 2, the spaceship plan. Got it. So, which is better? My gut says the spaceship seems safer, more controlled.
A lot of people might lean that way. Advanced tech, maybe less risk than moving a whole planet. Others might say moving Earth saves everyone, potentially. But based on the principles and scale, what would Jeffrey West likely argue for?
Okay, given the topic, I'm guessing he'd go for moving the whole planet, the Wandering Earth.
Almost certainly. And the reasons why reveal three really key principles about how organizations, how humans, systems scale up.
All right, let's hear them. Principle number 1.
Principle one is that scale leads to efficiency. It's called sublinear scaling. Basically, as an organization gets bigger, its infrastructure needs grow slower than its size. It becomes more resource efficient per person.
Slower. So bigger is cheaper in a way. Can you give an example?
Think about cities. The total length of roads needed, or the number of gas stations, or the amount of electrical wiring, these things don't double if the population doubles.
They don't.
No. The data shows infrastructure scales with population to the power of about 0.85.
Yeah.
So less than 1.
Okay, 0.85. Well, what does that mean practically, like for the gas stations?
Right. It means a city of, say, 2 million people doesn't need twice as many gas stations as a city of 1 million. If the 1 million city has 50 stations, the 2 million city might only need around 80, not 100.
Ah, I see. You get more bang for your buck with infrastructure in bigger places. So moving the whole Earth leverages existing infrastructure much more efficiently than building a new spaceship from scratch.
Exactly. That's the efficiency argument. Now, principle two flips this around. It's about output.
Okay.
Principle two, scale accelerates output. This is called superlinear scaling.
Yeah.
Here, as the organization gets bigger, its output, things like innovation, wealth creation, increases faster than its size.
Faster. So bigger isn't just more efficient, it's also more productive per person.
Yes, significantly so. Take patents filed in a city or its overall GDP. These scale with population to the powers of about 1.15.
So more than one this time.
Right, which means if you double the city size, you get more than double the patents, more than double the economic activity.
That explains why people flock to big cities. More opportunities, higher salaries often. It's where the action is, the innovation.
It's a huge driver. You get higher output for relatively lower infrastructure costs per person. So from this output perspective, the Wandering Earth plan wins again. The sheer scale maximizes that accelerated productivity.
Okay, efficiency and accelerated output both favor the bigger system, the whole Earth. But what about the spaceship? Couldn't you just build a really big spaceship, maybe city-sized? Does size alone guarantee success?
That's where the third principle comes in, and it's arguably the most important. Principle three, diversity fosters vitality.
Diversity, how does that fit in?
The argument is that the real strength of a large human system isn't just its size, but its complexity specifically, its capacity to hold and benefit from diversity. And diversity here means individuals maintaining independent thought, different perspectives, different skills.
Okay, so it's not just about having lots of people, but lots of different people thinking differently.
Precisely. There's a classic experiment that shows this. Guessing the number of beans in a jar.
Right. I know this one.
If you let a group discuss it, they tend to converge on an answer, often influenced by strong personalities. Less diversity in the final guess. But if you have everyone guess independently, and then average those guesses.
The average is usually much closer to the actual number.
Exactly. The wisdom of the crowd. But it only works if the crowd maintains its diversity of thought. Strength in numbers requires independence.
Okay, so how does this apply to Wandering Earth versus spaceship?
Well, think about the spaceship scenario. To survive in such a confined, artificial, high-stakes environment, you'd likely need intense, maybe even militarized, training strict rules, uniformity, everyone following the same protocols.
It would probably suppress individuality, suppress diversity for the sake of order and survival.
Very likely. Whereas the Wandering Earth plan, by taking the whole planet, inherently preserves a vast amount of existing diversity. Different cultures, different ideas, different approaches. That diversity is a source of resilience, of adaptability.
So putting it all together, efficiency comes with scale, output accelerates with scale, but the real magic, the resilience and vitality, comes from nurturing diversity within that scale.
That's the synthesis. Bigness provides the foundation, the potential. But it's the ability of that large system to embrace complexity and diversity that makes it truly powerful and adaptable. It's not just about being big, it's about being a big that allows for difference.
So this whole journey through scale, it started with the inescapable limits on our own bodies, dictated by these deep fractal laws.
And it brought us to the potential of human organizations, which seem to follow different, even superlinear scaling rules, driven by interaction and diversity.
It really gives you a whole new way to look at growth, doesn't it? Whether you're thinking about your own life, a business, or society, it's like having a cheat sheet for the underlying patterns of the world.
It truly is.
Yeah.
Understanding these principles offers a powerful lens.
And it leaves us with a pretty big thought, maybe. If biological growth is fundamentally limited, kind of predetermined by these fractal laws, but human organizations, our collective creations, seem to scale with increasing returns, fueled by efficiency and diversity. What does that mean for where we're heading?
That's the provocative question, isn't it? Are we, through technology and connection, actually breaking free from our biological limits? Or are we just uncovering a new, maybe even grander, set of scaling laws that govern not just bodies, but maybe consciousness, society, information itself? What's the ultimate scale we're operating on?